Good morning, students. Rather, good afternoon.
Good afternoon, sir.
So, how was your mid-sem in chemistry? Question was quite easy. So, if you give attendance now in the chat box, it will not be recorded. So, unfortunately, so okay. Mid-sem was okay.
Yes, sir. Midsum was good.
Okay.
Yes, sir.
So, let us start. So, from today, we shall start discussing the second chapter of our syllabus, which is bonding in coordination compounds. And we shall discuss bonding in coordination compounds, which is only known as complexes, in terms of two theories, which are crystal field theory and molecular orbital approach. Now, in your school days, 11, 12, you have some idea about the bonding in coordination compound, particularly in terms of the valency bond theory. That is the in terms of hybridization, sp3d2, d2sp3, and sp3, dsp3, etc., depending on the coordination number, etc. Now, in this class, we shall exclusively deal with crystal field theory and molecular orbital theories. You have been exposed to some amount of crystal field theory, I am sure, in the 11, 12 also, but I think the amount of rigor there was relatively less. So we shall discuss CFT. And at the outset, I must make it clear that any question in the final sem regarding the bonding in coordination compounds has to be answered in using crystal field or molecular orbital. Instead of repeated warning, when it is found that at least few students, 10% of the students, they try to answer the questions in terms of hybridization. That means valency bond theory. Why I must make it clear, our syllabus includes CFT and MO. It does not include, or rather it excludes the valency bond theory. Hence, any answer using valency bond theory may not be entertained and you may not get marks, right? So please be very careful that any question on the bonding in coordination compound has to be answered using either crystal field or molecular orbital theory. Now, crystal field theory originally was proposed by the famous physicist Hans Bethe in 1929, and it was further expanded by Van Blake in 1935. And initially, this theory was proposed by Hans Bethe to explain colors of transition metal crystalline compounds, colors of the crystals of the transition metal salts. And he used a mathematical approach to the crystal field to discuss this crystal field theory. However, at that time, 1929, 1930s, at that time, the crystal field theory didn't attract much attention, particularly from the chemist, because at the almost same time, valency bond theory was being propagated and expanded by Linus Pauling, and Pauling was so much influential, particularly in the chemistry community, and relatively in terms of ease of understanding, valency bond theory was much easier to understand by chemists and other scientists compared to the much more rigorous crystal field theory. So, crystal field theory didn't attract attention of the chemists, and most of the discussion on the chemical bonding of metal complexes, coordination compounds, for the next almost 20 years, from 1930 to 1950, were predominantly based on the valency bond theory propagated by Linus Pauling, and later it was expanded by other scientists, valency bond theory, like say Slater, Mulliken, etc., who expanded the valence bond theory. So various very influential scientists like Pauling, Slater, even Van Blake, right? Mulliken, they actually propounded the valency bond theory, and it was the favorite theory for most of the scientists, particularly chemists, while discussing the chemical bonding in metal complexes. But gradually, particularly after 1940s, some disadvantages or some shortcomings of the valency bond theory became apparent. Most important shortcoming was explaining the temperature dependence of the magnetic properties of the complexes, how the magnetic properties of the metal complexes vary with temperature. That cannot be clearly explained by the valency bond theory. Color of the complexes, again, that means the optical spectra of the complexes. Again, valency bond theory was awfully short of any satisfactory explanation. And also, from the valency bond theory, though there were some explanation about the Yandler effect, about the distortion of the complexes, about the high spin and low spin complexes, whether it will be if you have a 4-coordinate complex, whether it will be tetrahedral or square planar. Valency bond theory regarding these points, though they offered certain explanation regarding say point 1, point 2, etc., but the explanations were not very satisfactory, was not philosophically or theoretically very satisfactory. For instance, if you have a 4-coordinate complex, whether it will be tetrahedral or square planar, that cannot be predicted by the valency bond theory. What valency bond theory tells us, that if it is a tetrahedral complex, it has to be explained by sp3 hybridization. If it is a square planar complex, it has to be explained by the dsp2 hybridization. Okay, but it cannot predict what kind of ligands can form tetrahedral complexes, what kind of ligands should have square planar complex, and what will be the energy difference, how to calculate the energy difference between the tetrahedral and square planar complexes, etc. That were not very well founded in terms of the valency bond theory. So these shortcomings of the valency bond theory became very apparent, and that's why people search for the alternative theory, right? For instance, I give you one example. If I take tetrachloride, okay, right? Say nickel tetrachloride, NiCl4 2 minus, platinum tetrachloride, PtCl4 2 minus, and PdCl4 2 minus, palladium tetrachloride. It was found that nickel, palladium, and platinum, they belong to the same group. Now, whereas nickel tetrachloride has got 2-electron paramagnetic moment, and it can be explained by the tetrahedral configuration of the nickel tetrachloride, but the platinum tetrachloride or tetrachloroplatinate or tetrachloropalladate, they actually are diamagnetic, and their bonding has to be explained in terms of square planar complex. But why they are behaving so, it was not very clear in the valency bond theory. So for all these different purposes, people search for the alternative theory, and then the theory of Btech, which was the crystal field theory, that gradually again attracted the attention. And in the 1950s, that means after 20 years of almost complete domination by the valency bond theory, in the 1950s, gradually the crystal field theory was being applied to chemical problem, and it was initially led by Hans Bethe and Van Blake, and later other scientists participated in the development of the crystal field theory. So what is crystal field theory? Crystal field theory, in the crystal field theory, it is based on the symmetry of the complexes and symmetry of the d orbitals. And also, in the crystal field theory, original crystal field theory is based on pure electrostatic interaction. It is thought that metal can be considered, metal and ligands, all of them can be considered as point charges, and these point charges interact with the d orbitals of the metal ion, and depending on the arrangement of the charges, that means depending on the symmetry of the complex, they may interact with the various d orbital in a different manner, and as a result of this, there will be d orbital splitting, and that leads to a crystal field that is called the crystal field splitting. So it is a pure electrostatic concept. Now, in this slide, I have shown you the symmetries of the d orbital. So if you look here, dxy, dxz, dyz, dzx, and dx square minus y square, all of them contain 4 lobes. As you can see, xy, so this is your x-axis, this is your y-axis, this is your z-axis. So xy is actually in the xy plane, and the 4 lobes are in between the x-axis and y-axis. And there are 2 nodal planes where the electron density is 0. This is the xz plane and this is the yz plane. So dxy has got 2 nodal plane, which is the xz and yz plane. This is the xz plane and this is the yz plane, right? Similarly, dyz, the 4 lobes are between z-axis and y-axis. So there are 4 lobes between y-axis and z-axis, and again there are 2 nodal planes. First nodal plane is your dxy plane. This is the basal plane, dxy plane. This is a nodal plane, and the other one is the dxz plane, right? This is the dxz plane, which is the nodal plane containing x-axis and z-axis, and this contains the xy, x, and y-axis. And finally, the dxz, it actually, the 4 lobes are along, or rather in between the x-axis and z-axis, right? And here the nodal planes are again, the xy plane is a nodal plane, this basal plane, and we have the yz plane as a nodal plane. So these 3 d orbitals has got 4 lobes. These lobes are situated in between the 2 Cartesian axes, either xy or yz or xz, and each of them contains 2 nodal planes. dx square minus y square, this actually is very similar to dxy, except for the fact whereas in the dxy the 4 lobes are situated in between the x and y axis at 45 degree. Here the lobes are actually oriented along the x and y axis, right? And so there are again 2 nodal planes. So here you have the nodal plane, which is the dyz plane, right? Here you have the nodal plane, and you have the 2 nodal planes which are at 45 degree between the x and y axis, right? So these are the 2 nodal plane. So one nodal plane is 45 degree here, and another nodal plane is here. And then finally, the dz square. Now dz square is got somewhat different orientation than the other 4. Here you have 2 main lobes, and there is a annular ring in the xy plane, and that these 2 lobes are along the z-axis. Now here you cannot find a nodal plane. Instead, we have 2 conical surfaces as drawn here. These are the 2 conical surfaces which are the nodal surface. So instead of nodal plane, we have to talk about nodal surface. And the general rule is that if you draw the angular part of the d orbital, these are the angular plots of the d orbital. If you draw the angular part of the d orbitals, they are angular part of any orbital for that matter, number of nodal planes or nodal surface will be equal to the L value of that orbital. So for S orbital L equal to 0, there will be no nodal plane or nodal surface. For each of the p orbital L equal to 1, so there will be one nodal plane for each of the p orbital, right? And L equal to 2 for d orbital. So for each of the d orbital, we expect two nodal planes or two nodal surfaces. Okay. Now, consider a metal ion which is situated at the center of a sphere, and suppose the sphere contains 6 negative charge. And according to your physics knowledge, you know this 6 negative charge in the normal circumstances, if it is a metallic sphere or like conducting sphere, then it will be uniformly distributed on the surface of the sphere. So there will be no localization of the charge. And as a result of this 6 negative charge will be uniformly distributed across the surface of the sphere. And if we consider only the electron-electron repulsion, then we may say that if this is the energy of the metal ion in the free state, that means when there were it was not surrounded by any charge, then on placing the metal ion at the center of a conducting sphere carrying 6 negative charge, obviously because of the electron-electron repulsion between the metal orbitals, particularly the metal d orbitals, all orbitals will be affected, but we are more concerned with the d orbitals here because that gives the splitting. So metal d orbitals, they will undergo repulsion with the negative charge, and as a result of this, the energy of the metal orbitals will increase because of the electron-electron repulsion. Now let us consider first of all an octahedral complex, because that is the complex which is most often discussed, right? And among the various metal complexes that are known today, probably 75 to 80% will belong to the octahedral complexes, right? So an octahedral complex, here I have told you, here we consider metal and ligands as actually point charges. So metal is situated at the center of the Cartesian coordinate and system, and we have 6 charges which are situated along the positive and negative direction of the 3 Cartesian coordinates, Cartesian axes, and they are equidistant. That means all the ligands are placed at equal distance. So you can see here, this has got coordinate equal to a0, 0. This has got minus a0, 0. This is equal to 0 minus a0. This is 0 a0, and this 0 0 a 0 0 minus. So all the ligands are situated from the metal at a distance of a, and they are located symmetrically along the positive and negative directions of the x, y, and z axis. So if I try to find out how these charges interact with the d orbital, then you can see that the s orbital, for instance here, if it is s orbital, it will have almost a symmetrical field. That means in all directions it feels equal repulsion with the ligand negative charge. So s orbital will not have any splitting. On the other hand, if I consider the d orbitals, say first of all dxz orbital, as you can see, each of the 4 lobes are situated in between 2 ligands. So this lobe is situated in between these 2 ligands, this lobe is situated in between these 2 ligands, this lobe is situated in between these 2 ligands, and this lobe is situated in between these 2 ligands. So each of the 4 lobes are situated in between 2 ligands. This is also true for YZ and XY. So in all these cases, as the picture shows, that none of the lobes of this XZ, YZ, and XY, these 3 orbitals, they directly confront any of the ligand charges. Rather, each of the lobe is situated in between two ligand, and as a result of this, they have less repulsion. On the other hand, if I consider x square minus y square orbital, which is situated along x and y axis, so x square minus y square, so you see each of these lobes directly face one ligand. So this lobe faces the positive direction of the x-axis, this lobe faces the negative direction of the x-axis, this lobe faces the positive direction of the x-axis, this lobe faces the negative direction of the y-axis. So each of these four lobes directly approach, frontally approach one of the ligands situated along the Cartesian axis. On the other hand, dz square, remember, in case of dz square, electron density in any one of these two lobes is more than the electron density in any one of the four lobes of the other orbital. So dz square here, the electron density is heavily situated between these two lobes, and you see here this lobe directly faces the ligand along z-axis, plus direction of the z-axis. This lobe directly faces the ligand situated along the minus, that is 0, 0, minus a, negative direction of the z-axis. And this annular ring, it faces the electronic charges of in the xy plane. So in other words, from this picture, what do you find? That because of the spatial symmetry of the ligand environment, x square minus y square and z square faces more repulsion because their lobes are frontally confronting the ligand charges, whereas the xz, yz, and xy orbitals, they are facing less repulsion, and as a result of this, we find why they are facing less repulsion, because their lobes are situated in between two ligands, so they face less repulsion. And as a consequence of this, we have this energy diagram with which you are very much familiar. So this is the free d ion. Initially, first of all, we consider that the charges are not localized, but they are delocalized over the entire sphere. So if it is a spherical symmetry, we have all the d orbitals being uniformly destabilized because of repulsion, and you have this picture where all the d orbitals are destabilized. Now we localize the charges according to this. So when you localize the charges compared to the previous picture, compared to the spherical charge situation, when you localize the charges, some d orbitals faces less repulsion, some d orbital faces more repulsion. Those d orbitals for which repulsion decreases, they like the xz, yz, and xy orbitals, they are called T2G orbital. T means triply degenerate and G means Gerardi. They have Gerardi symmetry. We shall discuss it later. And the other two d orbitals, which are called EG orbital, which comprises of x square minus y square and z square orbital, their energy is destabilized, right? So we have the d orbitals splitting into two sets. One is a triply degenerate set, which is designated as T2G, T corresponding to triply degenerate, and G corresponds to Gerardi. That means with respect to inversion, with respect to a point of symmetry, if you go to the d orbitals, then you have Gerardi. That means plus to plus, minus to minus, etc., right? So you have a Gerardi symmetry. We have a Gerardi symmetry. Now, from mathematical calculation, we can show that these 3d orbitals whose energy is decreased, their energy is decreased by an amount. If I consider the total splitting between T2Gs and EG as actually delta O, this is O means delta octahedral. Splitting is delta octahedral, or sometimes it is called 10 dq. 10 dq and delta O are identical. So if I consider the total splitting as delta O, then it will be minus 0.4 delta O for the amount of splitting. Decrease is by minus 0.4 delta O and increase is by 0.6 delta O. And if it is 10 dq, it has to be multiplied by 10. So destabilization here is by 6 dq and stabilization here is by 4 dq. Now, so D, it is D multiplied by Q. Remember, it is not D subscript Q. Now, what is dq? I have written it here. D and Q has got its own expression. You need not remember this, just for your convenience or for your understanding. I have written here D stands for this expression. 35 Z means the charge of the metal ion, right? Ze by 4a to the power 5, where a according to this nomenclature is the metal ligand distance, right? So D equal to 35 Ze by 4a to the power 5 and Q equal to 2e. Then this is called the average value of R to the power 4. I shall explain what do you mean by that. Divided by 100.05. Now question is what is R2 to the power 4? Now this 2 subscript corresponds to the L value of the orbital. So R2 means we are talking about the d orbital, because d orbital has got L value equal to 2. Now what this nomenclature means in quantum mechanics, this means average value. Now why do we talk about average value? Because in quantum mechanics, you know that the electrons cannot be, unlike the Newtonian mechanics where electrons are localized, the metal electron, rather the nucleus to electron distance is constant. Here, according to the wave picture in the quantum mechanics or Heisenberg uncertainty principle, you cannot localize the electron in that way. So electron will be situated at any distance between r equal to minus infinity to plus infinity. So when you talk about the radius of an orbital, it has to be an average value of the electron distribution. So that's why we have this symbol meaning average value, and to the power 4. That means you are taking fourth power of the radius. I am repeating, it is R2 to the power 4 means it is the fourth power radius of the d orbital whose average value we have taken. So mathematically it comes that it is the average value of the fourth power of the d orbital radius. So if I multiply d by d and q and the energy gap is 10 dq, the total splitting is 10 dq, 10 dq will come as this value, 10 dq equal to 1/6 z square r2 to the power 4 by to the power 5. So you can easily see that the splitting, amount of splitting is dependent on the metal ion charge. If the metal ion charge is more positive, then the splitting will be larger. That means if I have a monopositive cation, dipositive cation, and tripositive cation, obviously as the positive charge on the metal ion increase, the splitting will increase. We find that it is inversely proportional to fifth power of the metal ligand distance. So if the metal ligand distance decreases, then the crystal field increases in a very rapid way, because it is inversely proportional to the fifth power of the metal ligand distance, and it is proportional to the fourth power of the d orbital, average value of the d orbital radius. It means that if the d orbital radius increases, the ligand field increases, the splitting increases. It means that if you go from 3D to 4D to 5D, so as you go from 3D to 4D to 5D, because of the increase of the n value, the average radius increases, right? So 3D orbitals has got shorter radius, 4D orbitals has got longer radius, 5D orbitals has got even longer radius. And as the radius increases, since the crystal field splitting is proportional to fourth power of the average value of the radius, so crystal field rapidly increases. So from 3D to 4D to 5D metal ion, crystal field splitting is expected to be rapidly increasing. Now, you are probably familiar with this picture. Now, forget about this, what I have written here, this you forget. You need not remember all these things, right? So you know that Eg corresponds to z square and x square minus y square orbital, and T2G corresponds to xz, xy, and yz orbitals. Now, if this situation is, or if this energy picture is the only energy picture to be considered, then you cannot explain why there is a crystal field stabilization. Because compared to free ion, according to this picture, compared to free ion, in any case, both T2G and Eg orbital has got higher energy. And so why metal ions should form a complex? Because T2G and Eg orbitals has got much higher energy than the free ion. So it should dissociate into free ion and the ligands. So in other words, this energy picture with which you are very much familiar, this is a partial energy picture where only electron-electron repulsion has been taken into account. Only electron-electron repulsion has been taken into account. Now, I have tried to draw the full energy diagram here. Unfortunately, because of the size, so these things may be small. I will read it out. So here, consider this is the free metal ion. And suppose gradually to the free metal ion, we are bringing the ligands from infinite distance. What will happen? Initially, there'll be huge fall in energy of the system because of the electrostatic attraction between the positive charge on the metal ion and negative charge on the ligands. So here, first of all, we considered this situation where initially we have started with the metal ion, and then we are bringing the 6 negative charges from infinite distance gradually towards the metal ion. So if initially we keep the spherical distribution, then there will be first of all electrostatic attraction between the positive charge on the metal ion and the electrons of the ligand, and so there will be huge fall of the energy of the system. And then when the metal ligand distance is sufficiently close, there will be gradual starting of the repulse. When initial phase, there will be no electron-electron repulsion, or there will be negligible electron-electron repulsion as long as the metal ligand distance is sufficiently long. But when the metal ligand distance comes to the bonding distance, when the electrons of the metal ion and electrons of the ligand start interacting with each other, we find there will be increase of energy of the system because of the repulsion between the electrons of the metal ion and electrons on the ligand. And this electron repulsion, we have split it up into two cases. One is, this is the electron-electron repulsion between ligand and the valence, between the ligand electrons and the valency orbitals of the metal ions in the spherical field. This one, except the d orbital, and we have considered the d orbital specially in this way. So in this two step, the electron-electron repulsion increases the energy of the system. This is the this part is the electron-electron repulsion between the metal electron, all the metal electrons except d electrons with the ligand, and this corresponds to repulsion between the d electrons and the metal ion. So here we have the picture, right? And finally, because of the instead of spherical field, when you have a octahedral crystal field, you have a splitting into T2G and Ag with the -4 dq and +6 dq. So now you can see in this picture, compared to free metal ion, both T2G and Ag has got lower energy. And this will explain why the complex is stable when electron is either in the T2G orbital or Eg orbital. So this is a partial energy picture which depicts only the electron-electron repulsion. This is a full-blown energy picture where we have both the electrostatic attraction and repulsion as well as the crystal field splitting. All of them has been taken into account. So this is a more complete picture that is for your satisfaction again, because otherwise the question, at least when I started reading the crystal field theory initially, I was unconvinced why metal complex is stable, because for all the pictures in the books, it appeared that compared to free ion, the d orbital has got higher energy, much higher energy, and so there was no justification why it should be stable. So this picture clarifies the stability of the complexes, and really all the d orbitals has got lower energy than the free ion when it is in the complex state. So this explains the crystal field splitting in an octahedral field. Now, before proceeding further, I must again tell you that very often in chemistry books, the importance of crystal field splitting is overstated, in the sense we overestimate the importance of the crystal field splitting, and we try to explain almost everything in chemical bonding in metal complexes using crystal field. But modern theory tells us, or modern calculation shows, that real bonding, the strength of the bonding, mainly comes from the overlap of the s and p orbitals of the metal ion with the orbitals of the ligands, with the appropriate symmetry orbitals of the ligand, which we shall discuss during the molecular orbital theory. And crystal field splitting offers at the most 10 to 15% of the total bonding energy. So you must remember, though crystal field theory can be used to explain various phenomena of chemical bonding and properties of metal complexes, but we must know, when we apply any theory, we must know its shortcoming. And the shortcoming of the crystal field theory is that its limitations should be understood, and it is that it contributes only 10 to 15% of the total bonding energy in a metal complex. Remaining around 80% of the bonding energy in a metal complex is provided by the covalent overlapping, the covalent bonding between the metal ligand orbital overlap between the ligand orbitals and the s and p orbitals of the metal ion. Now, before proceeding further, if you have any question up to this point, you can ask. Any question here? Any question? Okay.
No, sir.
So next question is that, okay, we have said that there is a crystal field splitting and its amount is delta O or 10 dq. Next question obviously comes into our mind, that how to measure 10 dq or how to measure delta O. Is there any experimental way of directly getting the value of 10 dq? Yes, we can do that. And this is shown in this picture. Suppose we have the simplest of the system. We have a D1 system, right? We have a D1 system. So D1 system, so this is the T2G orbital, this is the E orbitals, and in the ground state, we have one of the electrons occupying the only one electron that is there in the system. It is occupying one of the T2G orbitals. Now we supply energy to the system, appropriate energy to the system, H nu, electromagnetic radiation to the system, and as a result of this, there is absorption of radiation, and the electron is promoted from the T2G orbital to the E orbital. So this is the excited state configuration, whereby one electron, which was initially in the ground state, belonged to the T2G orbital, it has jumped to the EG orbital. So obviously, this energy gap, it is 10 dq. So if I can measure what is the energy frequency that is required to promote an electron from a T2G to E orbital, that will correspond to 10 dq. So in other words, in order to measure 10 dq, one of the easiest way is to measure is to record the electronic spectra of the complexes. Now for D1 system, it is quite easy. For D2, D3, D4, etc., for multi-electronic system, the things are more difficult, but it can be done. Why things are more difficult? Because there, when you have more than one electron, the electron-electron repulsion comes into effect, and so when you promote an electron from a T2G orbital to a E orbital, along with the crystal field splitting, the change in the electron repulsion between two electrons, when two electrons are situated in the T2G orbital, and suppose when one electron is in the T2G orbital and another electron in the E orbital, there will be change of electron repulsion, and that has to be taken into account while counting the promotion energy or while calculating the 10 dq. But in any case, it is not very difficult, and with some effort, one can learn and understand how to tackle even the multi-electron system. So the electronic spectra which we am talking about is something like this. So here we have plotted in the x-axis the frequency, that is nu bar rather, in centimeter inverse. So h nu equal to hc nu bar. So here frequency in centimeter inverse plotted in the x-axis, and y-axis we have plotted the intensity of absorption in terms of the epsilon value. I think organic chemistry, they are teaching you in the UV visible spectroscopy what is the molar extinction coefficient, etc. So you have taken the log of the molar extinction coefficient, and it gives a peak around say around 500 nanometer, right? 500 nanometer. This is the top bar is in nanometer, and the bottom line is in centimeter inverse. So it corresponds to 20,300 centimeter inverse. Beside there is another small peak here, but for the time we are neglecting. So there is the main band is around 20,300 centimeter inverse. So you may say that the energy gap between the T2G and E orbital is equal to 20,300 centimeter inverse, or we can convert it to the other units using the formula that 1000 centimeter inverse equal to this much of kilojoule per mole, or this much of kilocalorie per mole, or this much of electron volt. So using this conversion formula, we can convert this energy into either kilojoule or electron volt or even kilocalorie, etc., etc. So we can, in other words, in short, what I wanted to emphasize here is that it is very easy to measure experimentally the 10 dq value. They can be measured experimentally easily using the electronic spectroscopy of the complexes. Next, we consider that the crystal field splitting, which was shown as 10 dq here, right? 10 dq. What are the factors? Because this question very often comes. What are the factors that affect 10 dq? Now, the factors that affect 10 dq can be classified under two headings. One, the factors related to the metal ion, and second are the factors related to the ligand. First of all, let us consider the factors which are related to the metal ion. So as I have already told you that since 10 dq is proportional to Z, so as the charge on the metal ion increases, we should expect 10 dq or crystal field splitting to increase. And so for a given metal ion, say iron, if I take ferrous and ferric will have higher crystal field splitting than ferrous, right? Similarly, if I take manganese 2 and manganese 3 will have higher crystal field splitting than manganese 2, etc. So for a given metal ion, as the charge on the metal ion, that is the oxidation state of the metal ion increases, 10 dq increases, and it has been generally found that the divalent ions of the first transition series 10 dq value are lying between 700 to 3000 centimeter inverse, whereas for trivalent ion it increases to this much. So the range is 1200 to 3500, 3500 centimeter inverse. So clearly the experimental data supports the theoretical contention that as the positive charge on the metal ion increases, the 10 dq value will substantially increase. Then across a period 10 dq will increase. That means if you start for any given transition series, as we move from left to right, what will happen? The nuclear charge increases, but we know that spinning does not increase much. So effective nuclear charge on moving from left to right increases, and effective nuclear charge increase means, first of all, the Z effective increases, and moreover, since the radius decreases, so if the radius decreases, the metal ion radius decreases, the metal ligand bond length decreases, right? So that means the ligand can approach the metal ion more closely as we move from left to right because of the shortening of the metal ion radius. And as a result of this, we find that across a period, both because of the increase of effective nuclear charge and decrease of the radius of the metal ion, the 10 dq will increase. Finally, down a group, that means if I move from 3D to 4D to 5D, again I have told you that from 3D to 4D to 5D, the average radius increases, and if the average radius increases, obviously the crystal field will increase. So down a group 10 dq increases. So moving from first to second transition series, we find 10 dq value increases by 50%. So substantial increase on moving from first transition series to second transition series. We find that the 10 dq value increases by 50% because of the increase of radius of the d orbital, 4d orbital compared to that of the 3d orbital. Again, on moving from second to third transition metal ions of the same group, 10 dq value further increases by 25%. There is another 25% increase from 4D to 5D. Now, why from first to second there is substantial increase, and from second to third there is a less increase? Because in between second and third transition series we have the lanthanides, and because of the lanthanide contraction, the radius on going from 4D to 5D orbital, the radius of the orbital does not increase as much as in case of 3D to 4D because of the effect of the lanthanide ion. That means because of the effect of the increased effective nuclear charge. So from second to third, the increase of radius of the d orbital is much less compared to that from first to second because of the effect of lanthanide contraction between second and third transition metal ion. And so as the increase of radius, percentage increase of radius decreases, so you find that the 10 dq value increases by only 25% on moving from second to third, and by 50% on moving from first to second. So I shall stop it here, because the next thing is the ligand related factor, and that we will discuss in the next class. So if you have any question up to this point, you can ask me. So many of the things which I have said is already familiar to you. Maybe we have added some more data here or some more information here, but more or less you know whatever I have discussed today under school chemistry knowledge. Right? It may not be so detailed as I have discussed here, but you have a general flavor of the things which I have discussed today. Right? Maybe some quantitative information was missing, but you have some flavor of whatever I have discussed today in your school chemistry. Okay. So if you don't have any question, we can leave. Okay.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.